In this next series of lectures, we will be deriving the radiation from a magnetic dipole. Okay. And like I said, this next series of lectures, this is actually going to be kind of a drawn-out derivation, so it's probably going to span about 3 different videos. So this is just part 1. And so what we're going to do is we're going to define what the magnetic dipole is. Kind of the simplest example we can use is, let's imagine that we have a ring of current that is essentially sitting in the XY plane. Okay, so this current is oscillating back and forth. And so we can write the current with respect to time as some magnitude I0 cosine omega t, where omega is the driving frequency of the current. I mean, you can almost consider it as an alternating current, like an AC current. Okay. And so the so the dipole moment, the magnetic dipole moment, is m as a function of time, which is the area pi b squared. So it has some radius b to our loop times the current, and it'll be pointing in the z direction. So our magnetic moment is actually going to be pointing up here, like this. Okay, so we can write this out then as pi b squared I0 cosine omega t in the z direction, and we can rewrite this as just some magnitude of the magnetic moment, m0, which is essentially this quantity right here, times the cosine of omega t in the z direction. Okay, so let's put some more parameters to this. And so what we're going to do is we are going to measure the magnetic field and the electric field at some point in space out here. And I'm going to orient it in such a way that that point sits in the XZ plane. Okay, so this is purely an arbitrary choice, but I decided let's line it up with that plane in order to simplify the math a little bit. So that is our distance r from the origin to the point in space where we're going to be measuring things like the potential or the field. Now the current element is right down here, and so that, I'll use a different color, the distance from the current element to that point in space is script r. The angle between the position vector r and the z-axis is going to be theta, right there. And then the phi direction is going to be in this direction, so I'll call that phi prime. The length of this current element is dl prime, so because it's primed because we are associated with the current element. And last but not least, there is an angle, a psi, so I'll draw it in blue, between the radius of the circle of the loop and our position vector. So that's the angle psi. Okay, so now we've written out all of the parameters to the problem. We can now put them into equations. Okay, so the first thing we can note is that there's no free charge So Q is equal to 0. And it also implies that V is equal to 0. So there's no electric potential because there's no charge. The magnetic potential, A, we can write out as μ0/4π, integrating now over the current. And we're going to rewrite the time as the retarded time. And we're going to integrate that over the length dl prime. Okay, where dl prime is the radius times the cosine of phi prime d phi prime in the y direction. So how did I get the y direction? Well, I got the y direction because I decided to put my point that I'm measuring in the xz plane. So therefore, I'm basically projecting it onto the y-axis. So that component of it. Okay. Or another way of saying it is that the x components cancel. So a fortuitous choice of where I'm placing the point in space that I'm measuring all the fields, and basically the x components cancel, and the only component that adds up, sums up, is in the y direction. Okay, so now I can write out this r, script r, using the law of cosines, as r squared plus b squared minus 2rb cosine psi. The r vector is r sine theta in the x direction plus r cosine theta in the z direction, because I put it in the xz plane. B is b cosine phi prime in the x direction plus b sine phi prime in the y direction, because the circle is in the xy plane. That loop of current is in the xy plane. And so if I put these together, r dotted into b, now in Cartesian coordinates, gives me rb sine theta cosine psi plus 0 times b sine phi, because there's no y component to r, plus 0 times r cosine theta, because there's no z component to the b vector. So in the end, what I get is r b sine theta cosine phi prime. Okay. Now we may need later r dot, another way I could write this r dot b is I could write it now using the psi angle, which is just rb cosine psi, which is essentially, all we're doing is relating the psi and the phi. So anyway, so that way I don't have to use psi anymore. Instead, I'll just use for psi, I'll use sine theta cosine phi. So that would give me r squared plus b squared minus 2rb sine theta cosine phi prime square root. Okay, so all I did in that exercise was to eliminate using the angle psi. I want to use everything now in spherical coordinates of r, theta, and phi. Okay, so now let's apply one approximation. So our first approximation number 1, is that the radius of this loop is much, much smaller than the distance that I'm measuring to. So from this far away distance, that radius looks pretty small, you know, almost considering it, you know, we could consider it not to be a loop, but almost a point. But we're going to be far enough away that we don't have to worry about that. So in that case, now what I can do is I can drop out the b squared term, and so r is approximately r squared minus 2rb sine theta cosine phi prime square root. And now if I use the binomial expansion, r is essentially, let's see. Oh, but first I want to factor out an r squared, so I get r 1 minus 2b over r sine theta cosine phi prime. Now I use the binomial expansion on the square root. And what I get is r is approximately r 1 minus 1/2 times 2b over r sine theta cosine phi, like so, or r is approximately r 1 minus b over r sine theta cosine phi prime. Okay, so what we really need now is 1 over that r. We're going to need that later on. And so we could do the same procedure that I did above, and what I would get is 1 over r is approximately 1 over r. And the only difference between doing the binomial expansion when it's the square root of something or 1 over the square root of something is that you change the sign. Okay, so now I've written out my now I've written out expressions for the distances r. Okay, so the last thing I'm going to do in this video now is take a look at the cosine of omega t minus r over c. I can write out as cosine omega t minus r over c, because that's from the 1 right here. And then I would have plus omega b over r I'm sorry. I'd multiply it by r, so that would cancel. Okay, so when I multiply out the r through, then I would get rid of that that r, and so I'm left with then is just the c, and that would be then sine theta cosine phi, like so, phi prime. And then I can break this up with a trig identity into the cosine of omega t minus r over c times the cosine of omega b over c sine theta cosine phi prime, squeeze in there, minus the sine. Okay, so I'm going to stop here, and in the next video lecture, we're going to continue this and see what other approximations we can make.